So hi guys, so today we are going to start with the next topic, that is QLora. We have been talking about quantization and LoRa from a lot of months, right? From the point of papers have been released, and a lot of things have happened in the particular field and subject. So I thought, let's make a video about it so that we can understand the whole concept of QLora. So people who are familiar with I think the concept of quantization and LoRa, I think they can skip this part and maybe move directly to the tutorial part. And as usual, I will give the link to this notebook in the description section. You guys can go and check it from there. So yeah, let's start. So first of all, we need to do Hugging Face, CLI login. The reason is because we are going to download some models, and most of the models actually require, right, that you need to have the authentication to download them and use them. Similarly, we will need the bits and bytes, dataset, accelerate, LoRa lib, and the PEFT module. So these modules we actually need. So we will be using the Phi-2 model. So people who don't know about Phi, so this is the model Phi. So the Phi-2 model was released by Microsoft few months back, and it's a very good model. So this is, I think, only 3.2 billion parameters model, and it is outperforming almost similar to ChatGPT, right? That is Llama 70 billion, I think. Yeah, Llama 70 billion, they are able to perform like that. Not exactly, but yeah, very close to that. So it's a very good model. So it's very small model, so it's easy to load. So I have loaded it. So let's start it with it. So this is the bits and bytes configuration. So this is the library that we are using for quantization. So you see here a lot of terms you are seeing here, right? So let's actually first understand in a brief that what is exactly this whole QLora concept. So let's look at this slide. So if you see here, right? So I'll do the slideshow for ease. I think it's fine. Yeah. So this is the quantized part. So suppose these are all the things, right? So just understand them as parameters, right? So most models are made up of billions of parameters, right? So let's say the Llama 2 has 7 billion parameters. Similarly, every parameter is 32 bit. So then we need, for each parameter we need a particular size, right? So let's say I'll show you some basic calculation here. So let's say we have Llama 2 7 billion. So it has 7 billion parameters, as we know. So for that we will need 7 times 10 raised to the power 9 multiplied by 32, because it's a 32 bit one. And then obviously we are going to divide it by 10 multiplied by 10 raised to the power 9 again, right? So this is going to give us the amount of GB, that is 28 GB approx, right? So this is the amount of space we are taking for Llama 2 7 billion alone, right? So loading such models is very hard on a standard smartphone or a PC. Obviously not smartphone. So computers are slow at computing the floating point operations. You see here, these are the parameters, right? So if we compare them with the integer operations, right, multiplying and everything, we see the computer is pretty fast at that. So try to do 3 multiplied by 6, that is 18, very fast. But 1.6 multiplied by, let's say, 3.4, you're going to take time. Similarly, computers also are same in this. So quantization comes into the role. So these numbers and everything, quantization aims to reduce the total amount of that bits that are required to each parameter by converting those floating points to integers. So what happens this way? A model that normalizes, occupies 10 GB can be compressed in less than 1 GB. Similarly, if you see this, right, if I remove this part, obviously we are not removing whole 32, right? But if we remove it and take it to a bit small number, let's say 2, and obviously the number is going to reduce, right? It's pretty obvious. So that is how things are going to happen. So don't think like this, that quantization is like we are rounding off or we are doing any rounding to the figures. No, we are not doing that. Quantization speeds up the computation, as the working with smaller data types are obviously smaller, right, faster. So I will tell you a formula. So the model size is equal to the size of the data type, data type, that is multiplied by the number of weights. So this is the point. So you see this plays a very crucial role. If this is big, the whole model size is going to be big. If this is small, the model size is going to be small. Pretty straightforward, right? So this is what quantization do. So if you go through this paper, I think this is the paper, right? The quantization one, this LoRa. So they actually are doing different thing, but this whole QLora concept is, you know, applying quantization before LoRa. So don't think QLora as a single concept. It's like quantized LoRa. So we'll talk about LoRa definitely in the video. So what we are doing here, we are quantizing. So we are setting a particular range, you know. So let's say minus 127 to 27, and then we apply a particular formula that can be anything. So and then we get this particular number, and then we use these numbers for all the operations and multiplication. Now you must be thinking that how did we come from here to here? There is a particular formula using. So there are a lot of approaches. You can come from here to here. A lot of approaches are there, right? So there is asymmetric quantization, there is symmetric quantization. So what happens in asymmetric and symmetric, I will give you a brief. So suppose you decide a range that is alpha to beta, right? So by using 4 bits we can represent floating points from there, it's 0 to 255, right? So we are going to clamp all the numbers between a particular range, that is alpha to beta. So let's say 0 to 255 we are doing. So what we are going to do, we are going to apply a particular formula. If you read that quantization paper, that formula looks something like this. I'll show you. So let's say this is x. So we are going to clamp the x, that is the t, xt, let's say divided by s plus so this is an absolute value, right? So this is an absolute value. So this divided by s plus 2. So this whole thing is going to happen inside this, and this s is equals to the range that you have decided, that is alpha minus beta divided by 2 raised to the power n minus 1. So n is the number of, you know, all the parameters and everything that is there. So that's the whole thing, right? So it's pretty straightforward. So if you are doing this, so this particular range get converted to this. So you can actually then dequantize it, but the point is, while dequantizing, it's a very tricky thing, right? When you are reapplying this formula, chances are you won't get exactly the same number, right? Because you have the precision here till every decimal, but you don't have that precision here. So when you are going to apply this, there's a chance you won't get the same number. So it's obvious basic math, right? Similarly, we have symmetric quantization. So what happens is that instead of alpha or beta you are taking, you take the biggest numbers, right? Definitely you will take alpha. So minus a to a. What is a here? So a is the highest absolute value, and then you apply the same formula to convert all the numbers. So here I think the biggest number is which one is, I think it's this one, right? So I think like this is the biggest number, I think 2484. So this number you take minus 24842 minus 2484. So you take this particular number and you know, apply the values like the previous formula only and get this whole matrix, right? So this is what we are doing here. So let's see. So this is the bits and bytes configuration. I'll take you to the Hugging Face page itself to make you understand what is this bits and bytes. So let's say this is the page. So if you go here, right, so you'll find a lot of things. I'll recommend you guys to go and play with it after the tutorial. So you see a lot of things are here. I am using only 4, but I want you guys to know about all of them. So this loading in 8-bit is pretty straightforward. So this is going to load the 8-bit. So I told you about 32-bit we have. So you're going to load in 8-bit. Then you have 4-bit. So you're going to use 4-bit. Then we have different also. That is double quant type, that is N4, NF4. Then the type of the data type that you're using. So we are keeping torch bfloat 16. So you are free to use anyone, but yeah, this is my recommendation to you guys, that choose it wisely. So I think this double quant, yeah. So this is as you can see, this is used for nested quantization, where the quantization constraints from the first quantization are quantized again. So you know, this is a nested one. So you multiple quantization you see here, right? So as I told you, one happens here, then maybe inside this range also you can have one. So yeah, same thing. So we defined all these things here, load in 4-bit, the type of quantization we type and everything, and then inside this auto model for CowView LLM. So where we put here the quantization configuration as one of the parameters. the BNB configuration, and then we load the model, that is Phi-2. So when we put it, so the model will be loaded in that particular case only. So it's pretty straightforward, right? So we have loaded this whole Phi-2 model here in a quantized version, that is 4-bit. Cool. So yeah, then I think we have to post process the model. So we have to post process the model to prepare it for that. So for that we use this particular from PEFT library, we have prepare model for k-bit training. So because we are not doing any direct training on this model, this is not a normal model, this is a quantized model, right? So we will need to prepare it, because we are not, this is a k-bit model, the k here is 4-bit. So we are going to do that. Now I think we can run this, and this is what it is going to do. It is going to import prepare model for k-bit and load it accordingly. So then we are going to see the number of parameters that are trainable in this. So this is just a function that I wrote here, not something very fancy. So now this is very important. Now we have quantized the model. Now we need to apply LoRA. So what is LoRA? So again, people who are actually familiar with this concept, you guys can actually skip it, because LoRA is, a lot of people are already familiar with this term, because LoRA has been, in this market for long. So yeah. So I think a lot of you guys must be knowing about matrix multiplication, right? So matrix multiplication has been a very essential part of this whole LLM training and inside mathematics part, right? So this, just look at this particular slide. You see the W delta here, right? So we are actually showing that this whole matrix can be made by just these two concepts. So if you see this cell, so if you get this by this by this, so this whole concept actually you can actually get by just multiplying. So this whole can be divided by 4/2 and 2/4. So to make the fine tuning more efficient, we use this approach LoRA to represent the weight updates with two smaller matrices. So these are called update matrices. So throughout the this whole concept, so these new matrices can be trained to adapt to the new data while keeping the overall number of changes low. We'll keep this, but this is important. So now let's deep dive into the paper. So you see here, right? These are the pre-trained weights, and this is the LoRA applied. So these two then can be added, and then we get a particular new matrix. So what are we doing? The original weight of matrix remain froze and doesn't receive any further adjustment. To produce the final results, both the original and the adapter weights are combined. So we just made a copy of these weights. Suppose you just made a copy of these weights, then you apply this formula, that instead of applying on this whole matrix, you are splitting them into two matrices, and then applying that particular weight change multiplication to these two matrices instead of this one. Now LoRA makes fine tuning efficiently by drastically reducing the number of trainable parameters. So it doesn't add any inference latency, because adapter weights can be merged with the base model, right? So these adapter weights that you get here, suppose you do this for one data, you can do this for another two data, third data, four data, five data, and you just keep this adapter weight with yourself. And let's say a customer says, I want a model from you that is specialized in English, let's say English literature. Okay, so you can give this particular weight one, which you have trained on English literature data. Then you want a customer says and say, okay, I want a model which is very good in biology. So you have one again set of weight LoRA adapter, which is good for that particular concept, and then just add them and present the model. So it's pretty good, right? So we are going to use the LoRA configuration from PEFT, and then let's actually look at this whole config library. I want you guys to feel that this is not very tough. You guys can just go and actually read documentations and learn a lot of things. This is how I also learned. So yeah, so you see here, so the first thing, let's start with the R. This is the rank. So the rank of the matrix that you are going to define here, LoRA and attention dimension. So these are the target modules. So this is optional. If you will leave it blank, it's fine. It is going to target all the modules, right? So here in this particular one, I am taking only these three modules. So you guys can go and have a look at the Phi model and look at all the modules, right? And the bias is none. This is, I think, also optional. It's fine, I think. So I think bias, yeah, can be none. Yeah. So it can be none. Then we have I think the next one is LoRa dropout. Yeah, dropout. So LoRa dropout, the probability for of dropout layers for the dropout of the layers. And then we have the task type. So this is I think our causal LM. And then I think there are different type of tasks, so you can adjust the model accordingly. The encoder only models will definitely have different tasks. So then you have this get model PEFT model. So what you are going to do, you are applying this on this model, this configuration, this particular LoRa configuration you are applying. So this model is now going to train in different way, obviously, right? So let's run this. So this is the number of trainable parameters, right? So we have freeze the weight. So now we have to just 42.8%, 0.42%. Yeah. So let's get this data set. So now you guys must be thinking, what is this data set? Let's go through the Hugging Face data set. So this data set is actually about English codes. See, this is the code, this is the author and everything. So yeah, it's just a very simple data set, not any hi-fi data set this is. So let's load it. So what we are going to do, we are for every data sample that is there, we are going to tokenize it, the code one, right? So it's quite easy. So yeah, now the tokenizer pad ID is equals to yes. This is optional actually, but not for this model, but yeah, I'm keeping it. So this is the model, the transformers.trainer. This is to train the SFT and everything. So these are the training arguments. The training data set we have already defined. Per device batch size, so we don't have a very strong GPU, and number of GPUs one only, so it's fine. We are keeping one. The warm-up steps are 2. The maximum number of steps are 10. So this is obviously going to the number of train epochs only. So learning it, we are keeping this. You can adjust this according to yourself. This is the float 0.16, and the logging steps is 1. The output directory I'm defining as outputs, and the optimizer is paged Adam 8-bit. Actually, you can keep this 4-bit also, but yeah, it's fine, pretty fine, right? So this is the data collator. So we have the tokenizer with us. So yeah, ML masked language modeling is false for now. So yeah, let's start it. So I think we are good to go. So while this is training, you will see actually the training is going to happen here, but yeah, it's going to set everything up. So we are silencing the warnings for now. We will re-enable them for inference actually. So let's start. So yeah, once that training has started, we can actually see the loss. So you see here, the training loss actually is decreasing only 3.32, then it's 2.4. I think by the last one it will reach I think okay, it's again increasing. Well, 2.85. So yeah, I think it will be 2.3 something in the last one. 2.25, yeah, was pretty close. So this is the training output metric. So the training loss was finally this. That's number of steps for 10. The training runtime was 24.3 seconds, I think, minutes, not seconds. I mean, the training steps per second 0.4. The operations that were done was this. The training loss was this. Epochs is this. Cool. So I think I have already pushed this model. So you guys can actually do this on your particular one. So you have to put your token here, right? So yeah, you can actually push this model to your Hugging Face hub. So before pushing, you need to create a repository there and just mention that repository name here, and your model will get pushed here. Now you must be thinking, why are you pushing it here? So actually I'm pushing the whole adapter here. This LoRa adapter that we trained on this whole model. So now actually we can load this model. So we can actually directly load this adapter. So this is the adapter ID, right? So what are we going to do? We are going to take this ID. This is the configuration from the model, and from the configuration we can actually get the base model. So what are we going to do here? We are taking the base model from this because it is in the backend keeping the obviously configuration of the base model, that is Phi-2. So I name this fine tune Phi as the adapter name. So I am first loading my whole main model. This is the main model, right? And then this is the tokenizer of the model. Now I am going to merge the LoRa model in this. So PEFT model from pre-trained this. So what is going to do? This is actually adding the weight and everything of that. So yeah. So what are we going to? We are doing here same step that we are doing here. Where is it? Yeah. So there is a merge function also. Peft also has a merge function that also is used, so in a different case. So that also we can maybe explore in future, but for now let's do this. So I'll clear this for ease. Yeah. So I think it's loading the checkpoint because it's deprecated. Please use bits and bytes configuration. So yeah, actually I use the configuration here. I think load in 8-bit true. That shouldn't be the case. Actually we just need to copy it, right? So we can just copy it here, and actually it's already in that case, so it's fine. I think we don't need to do this. I don't know. I think I was looking at something else and I just copy pasted it. Anyways, I'll fix that. So yeah, I think we have loaded our model, and we have even did this part. We just took the weights. Where is that? Yeah, we just took the weights and the pre-trained weights and the adapter and just combined them, right? So yeah, I think we can test it. So let's ask it a question. The capital of India is. So let's see how it responds. So this is the model that we have trained. So let's see. Actually it won't do anything different because this is not related to this, but let's see. I'll I think I'll copy this. Be yourself, everyone is already taken. Okay, so the capital of India is Delhi, Mumbai, Kolkata. Solution is A. Okay, this is a very generic thing, right? The Phi model could have done this. So let's see what it replies to this. Oh, okay, it is just saying fill in the blanks. Okay, cool. So I think you guys can play with it about this dataset. So many books, so little time. So I think let's ask it. So many books, so little. Let's see what it responds to this, because it's a causal model. We can't expect a lot of things from it, and it's already quantized. So you will see some uh, you know differences in the output type, right? So actually, so the number of books is less than number of pages. Okay, I think it's hallucinating right now, so it's fine, but yeah, it's pretty good. So one thing we need to make sure that every time that we are dequantizing it, you see here, right, the values are not the same. So you will obviously while quantizing you will definitely see some problem, or like let's say lack in the results. The output won't be the same it used to be. There will be some accuracy error, right? So you are compromising your accuracy in this case, but most of the cases it won't matter much, but yeah, it will sometimes. And I took the worst case, that is load in 4-bit. Obviously 8-bit will is definitely going to perform better in this case. So yeah, this was quantized LoRa. So yeah, LoRa and quantization are two different concepts, but we combined them here to see how things work here, actually to cover the both concepts in a single video. So I'll link the notebook and the paper to you guys in the description section. You guys can go and play with the notebook and just suggest anything you guys find useful and good. So yeah, so that is it for the video. Thank you guys, have a nice day.